Hello everyone, today we're looking at 4.6 day 2, and this is graphing tangent and cotangent. We're going to look at the parent function here at the top, and then right below that some other details about the characteristics, and then at the bottom of the page there an example. So we'll go through one of each of these. So here we're starting off with tangent. Now, when we were learning about our trig functions, we talked about even and odd functions, and so you might not remember those details, but this has to do with symmetry. If it's even, we have a symmetry about the vertical axis, and if it's odd, it has rotational symmetry. Which one will tangent be? Well, actually, let's graph it, and then we'll come back and answer those questions. We'll find out. So take a look here. I've got a little bit of the unit circle already set up. And so you can see that we're doing more than just the quadrant angles. We are also doing these angles at pi over 4, 3/4 pi, and so on. So I have those angles and their coordinate points. So remember that we paired up the sine function with the y-coordinate and the cosine function with the x-coordinate. So tangent is described as being sine over cosine, or you can think of it like the y-coordinate over the x-coordinate on your unit circle. So that has some implications, because if our x-coordinate is ever 0, well, we're not allowed to divide by 0. We're going to get an undefined result. So the question is, when will that happen? So here are all of the angles of the unit circle I have sketched out here, just to look at some sample values. And let's see what happens when we find the tangent at each angle. So we're taking the y-coordinate and dividing by the x-coordinate. Now remember here, this x is not the x-coordinate. This is just the input, right? Our input is the angle of rotation. So if you want to call it tangent x, or if you want to call it tangent theta, the idea is that this symbol here is representing your input, which is the angle of rotation. So at that angle of rotation, what will be the y-coordinate divided by the x-coordinate? So at 0 pi, we have y divided by x, 0 divided by 1. Well, that gives us exactly 0. At pi over 4, you can see that the x and the y-coordinate are the same. So when you do that division, you get a result of positive 1. And then here, you have 1 divided by 0, and that's your undefined result. At 3/4 pi, we have, again, the same values but differing by a sign, so we would get a negative 1. At pi, y divided by x, 0 divided by negative 1 is just 0. At 5/4 pi, this is going to be a positive 1. At 3/2 pi, negative 1 divided by 0 gives us undefined. And then at 7/4 pi, again, same coordinates but differing by a sign, we get a negative 1, and then back to 2 pi, that's once again 0. So notice we have this kind of pattern here. We're going 0, 1, undefined. Negative 1, 0, 1, undefined. Negative 1, 0. The next number would be 1, because this is the sequence right here. From one undefined value to the next undefined value, these specific numbers in between go negative 1, 0, positive 1. So if we continue the pattern, negative 1, 0, positive 1, and we could keep graphing. So what we're going to do here is, on our horizontal axis, we're going to use a scale of pi over 4. So there's 1/4 pi. There's pi over 2. There's 3/4 pi. There's 1 pi. 5/4 pi. 3/2 pi. 7/4 pi, and lastly 2 pi. So we're going to plot these points on my vertical scale, just to give myself a little bit more space so we can see the points a bit more clearly. I'm going to skip every other grid line, so that will be 1 and that will be 2. That'll be a little easier to see. Okay, so at 0 pi we have a point at 0. At pi over 4 we have a point of positive 1. At pi over 2, it's undefined. So remember, with undefined, that means there is nothing graphed there because there's no output. So that's your vertical asymptote. And then at 3/4 pi, we're at negative 1. At pi, we're at 0. At 5/4 pi, we're at positive 1. 3/2 pi is undefined. 7/4 pi is at negative 1. 2 pi is back to 0. So this is the actual pattern right here. Between these two vertical asymptotes, this is our tangent function in its graph. All right, so that's one cycle. That's one period. But when we graph these, on the parent function, we always want to look at the one that's around the origin. So we don't want to use this one. We want to use this one. And this is only half of the graph, right? The other half is over here. So again, we're going to do a little copy and paste. We're going to take this little tail, copy it, we're going to paste it over here so that we have a complete graph around the origin. So these vertical asymptotes are every 1, 2, 3, 4 grid lines. So let's create another one. 1, 2, 3, 4 grid lines to the left. So in other words, that is going to be found at negative pi over 2. And then taking this little tail on the far right and pasting it here, we're going to have a coordinate point at negative 1 and then just kind of extend downwards like so. So what we're saying is that we want this right here to be our cycle. So that's one period. In other words, we're ignoring the second cycle because it's a duplicate of the first one. In our parent function, we just want one unique pattern, if you will. So we're only looking at this much of the actual graph. We're saying that's one cycle. So if you go from negative pi over 2 to positive pi over 2, that is a distance, that is a period of just 1 pi. So the period equals pi, not 2 pi. So that's different from sine and cosine. Sine and cosine had a period of 2 pi, but here we have a period of 1 pi because if we were to go into that second period, well, it'd just be duplicating itself. So we also have the jump. So remember we talked about the jump or the scale. So we take that period, we divide it into 4 equal parts, and each of those is what we call the jump or the scale. And again, here is our midline or axis. And here I stretched it a little bit taller so we would have a clear spot to place the point. But wherever that critical value goes, that is your amplitude. And again, the amplitude is always positive, so even if you are going into a negative point that you're plotting there, that's still the amplitude. So the amplitude is still going to set that vertical stretch between the axis, which is at the midline, which is where you'll find one of your critical values, and then the amplitude finds one of those critical values, and the amplitude in the other direction finds the other critical value. So here there's only 3 critical values and 2 vertical asymptotes on either side. So notice that each feature is equally spaced apart, and that's the jump or the scale. So notice that we are starting here at negative pi over 2. And we're ending here at positive pi over 2. So notice, again, that's different from sine and cosine because they always started at 0 and they stopped at 2 pi. And this is noticeably different. All right. So let's talk about where are these vertical asymptotes described. So they occur at regular intervals, and they're vertical lines. We have x equals something, and so that something is the interval. That interval goes from here to here, or from here to here. That distance is 1 pi. So we have pi times n. So that n is that repeated pattern, that repeated interval. So at 1 pi, 2 pi, 3 pi, but we don't start at 0. The first one occurs here at negative pi over 2. So negative pi over 2 helps us to describe where these vertical asymptotes occur. What that means is that my domain is all real numbers, but not here. Not here. So my domain is all real numbers, but I cannot plug in values that would end up on the vertical asymptotes. So these are the restrictions. And then the range is all of my outputs. Well, the arrows go down and the arrows go up. So up to positive infinity, down to negative infinity. So the range is all real numbers. There's interval notation for us. So we're going to be focusing on writing the equations of the vertical asymptotes on our graph. We won't focus so much on the domain and the range, but those are the basics. So just to answer that question again, is tangent even or odd? Well, we talked about it having some sort of symmetry. So if we take a look at our parent function here, here's my vertical asymptotes. Here are those critical values. And then there's my origin right there. If it was even symmetry, we would see it mapping onto itself when we do this, and it does not map onto itself, so it is not even symmetry. Let's rotate it around 180 degrees. And when we do that, you see that it maps onto itself. So that means it is an odd function. And so an odd function has rotational symmetry. All right, so that's a little bit about its characteristics. That's the parent function. So here in the middle section, they're just detailing a few other pieces that we have talked about here. How do we find the vertical asymptotes on the graph? Well, you have to figure out where you start and where you end. And like what we've done before with the sines and cosines, you take everything in the middle. So that includes all of the b and the c, and you set that equal to where the tangent graph normally starts, which is at negative pi over 2. That is a negative sign right there. So this is for the start, and this is for the end. Right? You take everything that's in the parentheses in the grouping symbols, that includes the b and the c, and you set it equal to positive pi over 2 because that's where tangent normally ends. So notice that your x-intercept, we're talking about this point here in the middle, your x-intercept is the midpoint between the asymptotes. So if you were to take this distance between the asymptotes and cut it in half, that's one of your critical values. And then if you cut each of those halves in half again, so here's the right half, you cut that in half, and that halfway point will get you your rightmost critical value. If you cut your left half in half again, then you'll get a critical value right there in the middle between those two. So that's what it's saying there on point number 2. Point number 3, so again, this is the pattern for your tangent function. Your tangent function is increasing from left to right, right? It goes up from left to right when my leading coefficient is positive. However, if my leading coefficient is negative, that means we have a reflection upside down, and that means it's going to fall from left to right. So that's the tangent in its parent function, and that's the reflected tangent. Okay, so let's go to our example here. We're going to graph negative 2 tangent of 2x. So my value of a is negative 2, my value of b is 2. We have no c and no d. So no horizontal shift, no vertical shift. The amplitude, again, is always positive, so take the absolute value of that a, which in this case is 2, but I want to remind myself to reflect. So I jot a little note down there. That's just my own little technique to keep track of that information. The period is, now this is where it's different from sine and cosine. With sine and cosine, we did 2 pi divided by b. But here, my period is just 1 pi. How do we know that? Because that's the distance from start to finish of one complete cycle. Even from here to here, that's a distance of 1 pi. So what we're doing is we're taking 1 pi and dividing it by the value of b, which in this case is dividing by 2. So pi over 2 is the period. And again, take that result and divide that into 4 equal parts. And that's the same as multiplying by 1/4. And so this will be our scale, our jump, our scale. That will be on these tick marks. So 1/8 of a pi, so there's pi over 8. There's pi over 4. There's 3/8 pi. We'll add in more if we need. We'll see which way we go. Now, on the notes, I forgot to include the start and the end, so let's add them in here. So this is my starting calculation. This is my ending calculation. So to do that, take everything that's in the parentheses. Well, there is no parentheses here, but we would be talking about anything that would include the b and the c, right? In this case, it's just the 2x. and you set that equal to where the tangent function normally starts. So again, it normally starts at negative pi over 2. So we're going to divide both sides by 2 to isolate the variable. So that gives us x equals negative pi over 4. To find the ending value, again, we take the 2x and we set it equal to positive pi over 2, because that's where the tangent function normally ends. Divide both sides by 2 to isolate the variable, we get positive pi over 4. So we're going to start and stop at these values. So on my horizontal axis, I want to make sure that I go down to negative pi over 4. So let me fill in a bit more here. Again, our scale is 1/8 of a pi. So on the other side of 0 is negative 1/8 of a pi, and then negative pi over 4. And then we have our starting and stopping values. Our axis, our midline, again, is that value of d, which in this case is 0. So there's no vertical shift up or down. Now, when we graph sine and cosine, we relied heavily on the box to find our critical points. We're not going to draw a box this time because there is no upper maximum, there's no lower minimum. It goes up forever and down forever, so we can't contain it. Instead, we're going to start off with the starting and the ending values, which will create the vertical asymptotes. We'll divide that in half to get the critical value there, and then we'll divide each half into half to get those other two critical values, and tangent is, again, increasing. So I'm going to start with my negative pi over 4, that's my leftmost vertical asymptote. And then we end at positive pi over 4, that's my rightmost vertical asymptote. So that's going to be my one period right there. So now we divide that in half to get that critical point that's right in the middle. And I, once again, forgot my vertical scale. We need that information, don't we? So let's just go by 1. So there's 1, there's 2. So now we're taking each half and we're dividing it in half. In other words, we're right at the jump value. We're right at that scale marker. So between the leftmost vertical asymptote and the midpoint, halfway between those two, we are right here at negative pi over 8. So at this place, we want to have this point. So we look at the amplitude for our particular equation. We want the amplitude. And where that amplitude crosses that marker, we want to put a point right there. So here, my amplitude is 2. So 2 spaces below, right there. So that's my point. And then on the right-hand half, here's the jump value of 1/8 pi. My amplitude is 2. So at an amplitude of 2, where that crosses this jump value, that's my point. Now again, we still have to apply the reflection, so I haven't forgotten that one. But this would be the parent function with a vertical stretch of 2 and a horizontal shrink as well. So I'm just dotting this in here. That's what we would have if we just had the graph without the reflection. But because of the negative sign, we need to flip this upside down. So that means this critical value, which is underneath the midline, has to in fact be above the midline. And this critical value, which is above, has to in fact be below. So this is the final result. And that's what this piece right here is for. You can see that again, if A is negative, then we're going to fall down as we go from left to right. So that's the pattern of our tangent graph upside down. So let's talk about this. There really is no max and there is no minimum because it extends forever up and down. So there's really no characteristics to fill in right there. But let's talk about the vertical asymptote. So again, there's two parts. The first part has to do with the interval. How far is it from one to the next? And then this is where we're starting. All right, so how far are we going from one to the next? We're going from a negative pi over 4 to a positive pi over 4. So 1/4 pi plus another 1/4 pi adds up to a grand total of 2/4 pi. So 2/4 pi is pi over 2. So pi over 2 times n to show that it recurs But it doesn't start at 0, it starts here, so we tack on this minus pi over 4. So that's an equation that would help us calculate every placement of the vertical asymptote. Okay, so now let's go to the cotangent. It's going to look very similar to what we're doing here. We're going to use this unit circle again because we're going to come up with another table of values to help us plot those critical points. So if you need to refer back to this, you can. I don't have it drawn here, but for the cotangent function, we're talking about now cosine divided by sine. So if we're on the unit circle, that means we want to think of it as the x-coordinate divided by the y-coordinate. That means we cannot divide when the y-coordinate is 0. So where does that happen? So again, I'm using that unit circle from the previous page. At pi radians, we would have an undefined result because my y-coordinate is 0 at 0 pi radians. That's what I meant to say, 0 pi. At pi over 4, we get 1. At pi over 2, we get 0. At 3/4 pi, we get -1. At 1 pi, we get undefined. Again, our y-coordinate is 0 at this place. 5/4 pi, we have +1, and then a 0, and then a -1, and another undefined occurring here at 2 pi radians. So let's plot this. So again, we're going to use pi over 4 as the scale. So pi over 4, pi over 2, 3/4 pi, 1 pi, 5/4 pi, 3/2 pi, 7/4 pi, and 2 pi. And on my vertical scale, again, I'm going to skip every other grid line, so I've got enough space here. There we go. So let's see what we have. So at 0 pi, it's undefined, so I have my vertical asymptote here at 0, and also at pi, and also at 2 pi. And then plotting these points at 1/4 pi, I have a output of 1. At pi over 2, I have an output at 0. And at 3/4 pi, I have an output at -1. So what we're seeing then is a descending pattern. Our cotangent graph is decreasing from left to right, and we'll see a similar pattern here as well. At 5/4 pi, we have +1. At 3/2 pi, we have a 0. And at 7/4 pi, -1. So again, notice how that, as we go around the unit circle, we actually see, when we plot the cotangent, we actually get these repeating patterns. So what that means for us is we, again, just want to use one of these for the cycle. So that's one period, and we'll ignore the other. And again, divide that into 4 equal parts. And each of those becomes what we call the jump or the scale. So again, you have your axis or your midline. And again, you have your amplitude. That takes you to one of those critical values. And you've got your amplitude in the other direction below the axis. That takes you to the other critical value. So the pattern is very similar. We still have 3 critical values between those 2 vertical asymptotes. Where we are starting now is, notice that we are starting at 0. And where we end the pattern, we are ending at 1 pi. So again, that's different from sine and cosine, which ended at 2 pi. And even this is different than tangent. We saw that tangent, if I take you back a page, notice that tangent, we are equally spaced on either side of that vertical axis. So we're starting at -pi over 2 and stopping at +pi over 2, and with an increasing pattern. Here we have a decreasing pattern starting at 0 and ending at pi. So, again, our vertical asymptotes are going to be at even intervals, at regular intervals of length pi. So this is pi times n. And notice we are starting at 0, so you don't have to write a +0, but that would indicate where we would start. So if we had a sort of horizontal shift, that first one would be indicated right here. So that means my period is 1 pi. My domain is all real numbers, but not at those vertical asymptotes, which occur here at pi times n. And then again, the range is all real numbers as well. So that's the parent function. Here are some of those details again. For your start, you set the b and the c, which is usually in parentheses, set that equal to 0. And then for your end, you take all of that and set it equal to pi. So when we have a leading coefficient that is positive, then the pattern is that our cotangent graph falls. That's what we saw right up there. But if we have a negative in front, that means we're going to reflect it upside down. So if you think about that, you're going to reflect it upside down, and that means it turns it into a tangent graph. So tangent and cotangent look very similar just by a matter of reflecting it upside down. So here's our example. Example 2 is what we're looking at here. We have 1/2 times the cotangent of x over 2. All right, so the a is 1/2, the b is 1/2. Remember, you want to think of this as if the value of b was in front of the x, like this. So that's how we know the b is 1/2, not the 2. And again, no c or d in these because we're really focusing on what the parent function looks like with just a minimal of transformations. Amplitude is 1/2. The period is, again, 1 pi divided by b. Well, in this case, we're dividing by 1/2, right? So we have pi divided by 1/2. So multiply by the reciprocal and you get 2 pi. Take that result and divide that into 4 equal parts, and that'll be the jump or the scale. So that's our scale on our graph. Pi over 2, pi, 3/2 pi, and 2 pi. And we'll add more if we need. Our axis is at 0 because the value of d is 0. And we want our start and stop. So again, on the notes, I forgot to include those, so here's my starting value. So we're going to take everything that's in the parentheses. You can represent it as the 1/2 times pi, or 1/2 times x, or you can represent it as the x over 2. And we set it equal to 0 because that's where cotangent normally starts. So multiply both sides by 2, and we are still starting at 0. To find where the pattern ends, take that x over 2, set it equal to 1 pi. Again, that's where the cotangent graph normally ends. Multiply both sides by 2, and so our graph will end at 2 pi. So again, the period should match the distance from start to end. So my starting value at 0 is my vertical asymptote, and also at 2 pi. And let me put that scale on there. So for my vertical scale, I'm just stretching it out a little bit so I have a bit more space, going every other grid line. So what we have now is an amplitude of 1/2. All right, so here's my midline. This is my axis. So that amplitude of 1/2, so there's 1/2, so it's a very small space upwards and downwards. So there's my 1/2. That's where we'll find those other critical values. So between the two vertical asymptotes, right smack dab in the middle, you have a critical value on the midline. Remember that our cotangent graph is going to be falling. So at pi over 2, we want the upper critical value at that amplitude value, and at 3/2 pi, we want the lower amplitude value. So what we see here is we see a vertical shrink, and so we have the left side and the right side, which are, approaching those barriers, but right there in the middle, it sort of levels out. I don't want to say it's flat. It's clearly decreasing there, but we had stretched our scale out vertically a bit, so it would be a very slow horizontal transition before it drops back down again. So let's find the equation of these vertical asymptotes. X equals, so find the span, find the interval between one and the next. So from 0 to 2 pi is 2 pi, so 2 pi times n. So every 2 pi it'll show up again. The first one is starting at 0, so we don't have to adjust for that. I mean, you can write a +0 if you like to keep track of it, but we don't have to show that plus 0. Those would be the two pieces that come together to write the equation. And that is our example.